Okay. So previously we learned how we can code, the training code using the PyTorch library. Okay. And I said to you, these 5 lines is very important and will not be changed regardless of the network and optimizer and loss function you use. Okay. And also I explained this MLP layers. And this MLP is the architecture that stacks multiple linear layers with the nonlinear function. And it can represent the nonlinear mappings between the input and output. And I also explained why we have to have this kind of nonlinear functions in the middle of the MLP, unless it will become huge simple linear regression, regardless of their time complexity. Okay. So we have to involve this kind of nonlinear functions in the middle. And indeed, this is the implementation of the MLP using the PyTorch. And you can see we stack multiple linear layers, and in the middle, we need to use this kind of nonlinear function. And you can feel that maybe these 5 lines of the training code is same as before when we implement the linear regression, and also same loss function and same optimizer we will use for that. Okay, but only the network architectures are changed. And this is the code for making some data. So we will generate 1,000 number of samples, and we will use the iteration number of 10,000. And this is the code for generating some random value for input X. Okay, so we will generate 1,000 number of random input, and also our output will be generated with this kind of nonlinear function. Okay, so we will generate 1,000 X and Y pairs, and those pairs are having between their input and output, they have relationships with this kind of formula, right? Anyways, we generate 1,000 XY pairs, and actually we'll train our MLP layers that can mimic this kind of nonlinear function. Okay, so the MLP layers that looks like this. First, there this W1, B1, W2. These kind of things are parameters. Okay, so they are randomly initialized. So regardless of which input we input to these MLP layers, it will produce something strange. Okay, it will produce some strange number, but we will train this MLP to meet this XY, their data of, inherent formula. Okay, so these MLPs are at the initial step, it will generate some random value, but it becomes to generate something similar to these nonlinear functions. Okay, so you will see. So so at the test, after training, using this code, you can train your net, which is the MLP. And then after finishing the training for 10,000 epochs, you will see that you will do some prediction. So for the prediction as well, you have to generate some 5 samples, okay? And also you will generate some corresponding ground truths for that inputs. And then you will also input those randomly generated input to our trained network. And we can regard this as our prediction, okay? So, and we will print out our ground truth and our prediction here. And this is the result. And you can find that, they are, the floating values are in continuous space. So it is very hard to make them same, but you can feel that their scales are becoming very similar. between this prediction and the ground truth. So indeed, you can see after training our MLPs using the PyTorch library with these 5 lines of code, our MLPs become similar to this nonlinear function. Okay. So are you guys following this? Okay. And we will now, from now on, we will do the same for CNNs, the convolutional neural network. So we will now use the same training code to train these CNNs, okay? And as I mentioned, I mean, between the CNNs, their inputs are RGB 2D image, and our output would be, I mean, the semantic labels that denote the classes, semantic classes, okay? And in between these input and output, any differentiable layers could be there, but because the convolution is differentiable operation and it is frequently used in image processing domain, the deep learning researchers are motivated to use those operations inside this deep architecture, and that is actually called convolutional neural network. So we actually have this kind of architecture between this input and output. And I mean, inside the CNN architecture, as you already learned, the first part, those are composed of the convolutional layers, okay? And they are also involving some of the pooling layer and also have some nonlinear layer, okay? So, I mean, convolutional layer, it is processing the 2D signals. So for example, the input image here is 28 by 28 by 1 dimensional image. So, I mean, at the earlier years, we are processing only the grayscale image. So the channel number is 1. But nowadays, we are using color images as the input to the CNN. So mostly the input, their channel number is 3. Okay, and also we are using, I mean, larger images compared to the early stage, but this is the early architecture, so their input size is very small, and their input is grayscale. Anyways, I mean, the first part of the CNNs that's composed of the convolutional layer, which can process the 2D signals. And they are tend to reduce the 2D image size, but increasing the channel size. So you can see this kind of 2D image size are gradually reduced, okay, while applying the convolutional layers. But you can see their channel numbers are gradually, I mean, becoming larger, okay? And then after applying several layers of convolutional layers, you can see this kind of flattening. So flattening means after applying several convolutional layers, you can feel like that those 2D signals are becoming reduced. So you can eventually make them as the one-dimensional signal. So if you are inside this shaped array, 7 by 7 by 64, if you flatten those signals into the one-dimensional signal, then you can make 3,136 dimensional one-dimensional vector, okay, having this number of coefficients inside. Okay, this is called as the flattening, and this is also the differentiable layer. So it can be used inside the deep architecture. So anyways, by reducing the 2D signals, at the end, you will flatten the signal to be like one-dimensional vector. And then the thing happened after that is you apply this type of linear layers, okay? So these linear layers are the operation that is suited for processing one-dimensional signal. So after applying several convolutional layers, you flatten the signal to make one-dimensional signal and then apply this kind of linear layers. Okay, you can interpret this as the MLP layers as well, because we also apply some of the nonlinear layers in between these linear layers. But anyways, the aim for this subsequent one-dimensional processing module is they eventually want to map this one-dimensional signal to this dimensional vector, which means the number of classes. Okay, this 10 here is number of classes. So there are 10 number of classes. So you eventually want to map this type of intermediate feature vector into number of class dimensional vector. And that is actually indicating the probability for each class. Okay. So CNN is originally designed for image classification task that try to figure out which object is inside this image. So this is the input image, and you process via the convolution layer and make it into one-dimensional vector, and finally map to number of class dimensional vector, which indicates the probability for each class. Okay, and by choosing the one dimension that have the maximum probability, you can classify, you can find actually the class for that specific image. Okay, that's the image classification task. So, so we normally call the former part that is composed of the convolutional layers as the convolutional layers, and the later part, which is composed of one-dimensional processing unit, is called as fully connected layers. So this is actually same as MLP layers. Okay, all the components are differentiable, so you can use the same code as before to train the overall network. So I'll explain that from now on. So this is actually the code that can, define your own architecture. Okay. So previously we used this type of code to define our layers. Okay, define our architecture. But explicitly using this kind of class object, you can define your own network. I think this is more systematic way of defining your own CNN network. So this is the name of the network. So, and also you are inheriting some PyTorch modules, okay? And actually there are two methods inside, okay? And before that you have to import the PyTorch library, okay? And after, you have to define these two methods. And maybe you are already familiar with Python, so you may also familiar with how to program OOP style, program the OOP style code in Python. And actually this is the class, which is the basic unit for the OOP. And when defining your class, you have to define the initializer, okay? And also, sometimes we call it as constructor, okay? And also we can have a few more methods inside the class. And this is actually role as the constructor. And it is called once when your network is initialized, okay? So this init is, you can think that as the constructor of the class. And also this is the, additional method that can define some, the attribute of the class, okay, some behavior of the class. And we can define it, how to forward the signals when given the input signal X, okay? So you have to define it here forward. And without using the PyTorch library, you have to also implement a backward and parameter update rule by yourself, by defining this forward rule and seeing their formula, you have to calculate the derivative of that by yourself and have to implement that in this part. Okay, so this might be the differentiation of the output with respect to the input, and this would be dy dissector, the differentiation of the output with respect to their parameters. But also, if your layer doesn't have any parameters, then you can omit this part. Okay, but thing is, when you use the PyTorch, you don't have to implement this backward function and parameter update rule by yourself, because as I mentioned, the PyTorch library, inside the PyTorch library, the automatic gradient calculation method, their algorithm is already implemented, and this type of algorithm is operating, not depending on the forward function. Okay, so this algorithm is same, regardless of the forward function. So they actually don't have to know about this forward function. Okay, they can apply iteratively to the, any kind of forward function to calculate their gradient. Okay, so you don't actually have to implement these backward functions or parameter update rule, but they are already implemented in the superclass of your MyCNN class, and you can just inherit that. Okay, they are automatically inherited, and you don't have to worry about that. Okay, so the thing you have to define is forward function, and backward and parameter update rule, they are automatically working. Okay, when you use the PyTorch library, that's very good characteristic when you use the PyTorch. Okay, so, and as I told you, this is the initializer, constructor. So they are once called when you make some new instance using this class. Okay, so normally in this constructor, the architectures are defined. So because we are implementing the CNN architecture here, so convolutional layers in the former part of the CNN and also the fully connected layers in the later part of the CNNs, you have to implement that. Okay, so for the CNN, for the convolutional layer, you have to stack multiple 2D convolutional layer with some nonlinear function and some pooling layers inside. Okay, that becomes the convolutional layers. And for the fully connected layers, you have to stack multiple linear layers that map the input one-dimensional signal to intermediate one-dimensional signal. Okay. Okay. So this is how the fully connected layers are implemented. So, anyways, in the constructor, you have to. Normally you have to define your own architecture. Then also these layers their parameters are randomly initialized when defining these functions. Okay, and you also have to define your forward function. So this is the initial input to the entire deep learning architecture. And first thing you have to do is you feed your own input image X to first part of the CNN architecture, which is the convolutional layer. And then you flatten that. So this output would be the intermediate 2D signals. And then you will flatten it to have same dimensional, dimension is different, but same number of coefficients inside. Okay, so for example, if this dimension would be 7 by 7 by 64, then 3,000 something dimensional one-dimensional signals are obtained by calling this function, and you will input those signals into this X layer later, and this would be your final output. And because you will use, the final dimension of this layer should be coincide to the number of classes when you try to do image classification task. So the final output would be this dimensional vector, okay, which denotes the number of classes, the class probability, okay. So this is how you will define your own architecture, CNN architecture, using the PyTorch library, okay. If you define your architecture using this type of class, then the thing you can do is the only thing you will do in your training code would be using this class, you can make new instance, okay? That would be your network, okay? And using the same loss function and same optimizer and same training code, you can actually train your network initialized here, okay? So this would be the training code. That can train this net architecture. But the only thing which is skipped in this code is how to load this X and Y data set. But we will see that later. Later part of this lecture. Okay, are you guys following this? So as I told you, this is the image classification task. So the data images are having predefined number of semantic classes. And also we are assuming that the images are having one main object inside. So we can classify each image according to this predefined number of classes, okay? This is the famous dataset, CIFAR 10 dataset, having 10 semantic classes, and MNIST dataset, each also have the 10 classes inside, okay? And Caltech 101, it has 101 classes, and ImageNet, which is very large data set, having 1,000 classes inside, okay? From now on, I have to also explain, some of the loss functions. So the thing we learned has been, MSE loss, which is the mean square error loss, okay? Which is actually same as the Euclidean distance loss, okay? So, you will calculate the distance between ground truth and your prediction using this type of formula. This is the Euclidean distance. Then it is called as you are using the MSE loss, okay? Error loss. Okay, but this type of loss is useful when you try to do the regression task, okay? So your output, you are wanting to achieve this kind of thing. So your output, you want your output close to the ground truth value. But this is valid when your output is having some semantic meaning. But especially for the image classification task, your output would be, some of the integer values. For example, for when you're dealing with this 10 class classification task, your output is some integer number from 1 to 10. Okay. So if the output is 1, then it is denoting airplane. If output is 2, then it is denoting automobile. And if the output is 3, then it is denoting bird, like that. So in the image classification task, the output itself is not having any meaning, okay? And also it is lie on some discrete space, which is different from regression task, okay? So when you train your network for the image classification task, you cannot use this type of MSE loss, but instead require some other loss functions, okay? And I will explain that first. And actually that is called as the cross entropy. loss. We will call that as the cross entropy loss. But we will see the basic cases first. Okay, I mean basic cases means we will first train the network that can perform the binary classification task. In the binary classification task, the labels are composed of only two labels, 0 and 1. Okay, I mean there are only two classes, and the class 0 and class 1. Okay, that is called as the binary classification task. And actually, for doing this binary classification, the simplest form of classifier is called as logistic regression algorithm. Okay, so sometimes you will be confused between this logistic regression and the linear regression task, because they are starting from character L, and they are also having same word regression. So sometimes you will be confused, linear regression and logistic regression. They are similar in that their basic blocks are this kind of linear equation, okay? But they are totally different, because linear regression is the simplest form of the regressor. I mean, they can actually do regression tasks. But logistic regression algorithm is doing the similar, but they are actually doing the binary classification task. Okay, even though their name has the regression, what they actually does is the binary classification. Okay, that's very important. And this is their functions. So I mean, this is the sigmoid function actually. So x is the initial input. So you can interpret that if you are given this formula, you can interpret this as first apply some linear, some of the linear layer first. There should have this parenthesis. Okay, you will first apply this linear layer first and apply minus sign. Not minus sign, because the sigma already have this minus. So after applying linear layer, you will apply the sigmoid function subsequently. That's the logistic regression architecture. Are you guys following this? Okay. And then when you apply the sigmoid function, as I told you, given minus infinity to plus infinity input signal, the output would be bounded to 0 and from 0 to 1. Okay, that's the characteristic of the sigmoid function. So this G output will be bounded to from 0 to 1. Okay, and then what you will do on this G value is you will threshold this G value. So if this value is smaller than 0.5, then you will regard it as class 0. And if the value is larger than 0.5, you will regard it as the class 1. Okay. So you have to train these layers, which have W and B as the parameters. Those W and B would be randomly initialized, and at the earlier stage, it will produce some random value from 0 to 1. Okay. But you want to train this W and B using some proper loss function, and you actually want to perform the binary classification. For samples from class 0, you want to get the value which is smaller than 0.5. And for samples which is from the class 1, you want to get Z value which is larger than 0.5. Actually, using this criterion, you want to get this parameter W and B. That's the logistic regression task. Okay, are you guys following this? And I will show you how we can train this logistic regression towards having this kind of characteristic. If you learn those logistic regressor using this loss function whose name is binary cross entropy loss, then this function will have this kind of characteristics. Okay, this is called as binary cross entropy loss. Okay, so actually these two are same thing. Okay, I will first explain that. Okay, so I mean here yn is the n samples ground truth. Y means ground truth value, and Zn is n samples prediction. Okay, as I told you, Z is meaning our prediction, and Y means the ground truth. Okay, this is meaning that when the samples n samples ground truth is 1, we will use this loss function. And when n samples ground truth is 0, we will use this as the loss function. Okay, so this is the definition of loss, BCE loss. But you have to feel that this actually two are same. Okay, when you input 1 to yn, then this part becomes 0. Okay, so only this part remains, and that would be actually this. Okay, it converges to this, and that's actually same for that. Okay, and also sorry. And also when you input 0 to yn, then this part goes 0, and only this part remains as this. Okay, and actually this form is same 0. Maybe because of this, it becomes like this. So minus sign retained. Okay, anyways, you have to feel that these two formula is same. Okay, for samples whose yn is 0, this formula becomes like this. And for samples whose yn is 1, this entire formula becomes same as this. Okay, so the two different format is same actually. And also you have to feel that, I mean, you also have to understand this. Okay. So this is the RNZN graph. Okay. And if you multiply minus, then that would have this type of graph. So this is the minus LNZN graph. Okay. And actually, you already learned that here their coordinate is 1, 0. Okay. So this is the characteristic of Ln function. So if their x value is 1, then Ln function should be 0. Okay. And I mean, for yn, which is when the ground truth value is 1, we will apply this type of loss function. So eventually, what we want to do is we want to make our prediction z close to our ground truth value. Okay, when ground truth is 1, we have to make it close to 1. Okay, and also by minimizing the loss. I mean, loss would be minimized always. Our optimizer make our loss minimized, okay? And you have to feel that when ground truth is 1, minimizing loss would be equivalent to make Zn goes close to 1. Okay, that is actually by interpreting this graph. If your graph minus ln Zn looks like this, then and also your Zn value is bounded to 0 to 1 range, because our Zn have the sigmoid at the last layer, okay? And you already see that their range would be bounded to from 0 to 1. So our Zn is bounded to this range, okay? So this range, when we try to minimize this loss function, then it would go this direction, okay? Then it is actually meaning that your Z values will be go to 1, goes to close to 1, okay? So actually by minimizing this loss, you will see your Zn will go close to 1. Okay, are you guys following this? Okay. And also the remaining part, if your yn is 0, by minimizing this type of loss, you will see the inner part of this log function would go close to 1, and it means your Zn would go close to 0. Okay, so when your ground truth is 0, by minimizing this loss function is equivalent to making your output Zn close to 0. Okay, so when your ground truth is 1, minimizing this loss is making your prediction close to 1. Okay, and when your ground truth is 0, minimizing this loss is same as making your prediction goes close to 0. Okay, so this is actually the loss function that can make your network to be act like what I mentioned here. So when your ground truth is 0, the Z value, your output value, should be close to 0. Okay, so if you threshold that using some mid level, because your output is from 0 to 1, this 0.5 is kind of the middle value. Okay, if you threshold that, if your Z values are already close to 0, then your by thresholding your output value, you can get this 0 class. Okay, and also when the ground truth value is 1, your Z, you have to make your prediction Z close to 1, and by thresholding that using 0.5, which is the middle value, you can predict it as class 1. Okay, that's actually the objective of this logistic regression function that can actually perform the binary classification task. Okay, and as I mentioned, this is the binary cross entropy loss having just 2 classes inside. Okay, and this binary cross entropy loss is already implemented in the PyTorch. So this is also for making some, how to say, the data. Okay, so by calling this type of function, you can load iris data set, which is also a famous machine learning data set. Okay, so you will, get some data X, okay, and choosing 100 dimension, and this Y would be some label, discrete label, which indicates the, the flower's name, their class, okay. This Y is somehow the classification label, okay. And this is the code for making them to PyTorch variable. anyways, you will load this X and Y data from predefined iris dataset. So X is some 100-dimensional vector having some defining some characteristics of the flowers, and Y is discrete integer label. Yeah. Anyways, loaded from this iris dataset. And you will see this code are same as before, okay? But now you will see this linear, I mean the layers. This is actually coincides with this operator. And then if you apply some sigmoid function after this net, which is actually the linear layer, then actually this becomes the, how to say, the function we defined, which is the logistic regressor, okay? The one we defined is like this, applying linear and applying sigmoid later. So this becomes our whole logistic regression network, okay? And then loss function, we will define it using binary cross entropy loss already defined in the PyTorch, okay? So you can use the same loss forward and backward functions for implementing this, and using the same gradient descent optimizer, you can train. Okay, this is actually the code that can achieve the logistic regression. Okay, and you can only change your network. Okay, and change the loss functions to implement the logistic regressor. Okay, this is easy, right? Any questions? Okay. And this is another way to implement the logistic regressor. So, I mean, here you implement it using BCE loss function. BCE read logistics loss. There is a loss function implemented in PyTorch. So this means the loss, when you apply loss, you apply the sigmoid first and apply the binary cross entropy loss afterwards. So I mean, this loss function already have this sigmoid. So here you don't have to implement your own sigmoid function as before. Okay. So anyways, this is the other way to implement logistic regressor in the PyTorch. Okay. Anyways, you can feel this implementation of logistic regression algorithm is become very easy using the PyTorch. Okay, and this is indicating that actually these two losses are doing the same thing. Okay, I will skip. Okay, so we see that we can train binary classification algorithm using the BCE loss function, and now we want to achieve the multi-class classification, I mean, training, okay? So, which means there would be multiple classes, I mean, inside the output, okay? But I mean, when you try to constitute the deep architecture, I mean, they are having multiple layers, and if you input X, sometimes it involves the convolutional layers, and later, when you do the flattening, it is also having fully connected layers subsequently, and then it should be mapped to the probability at the end of the network. But thing is, normally your network, their output scale is not bounded. Okay, if you apply Lello functions, for example, I mean their output scale is not bounded. Okay, it could have 0 to infinity scaled signals at the end. So, but I mean when you call some floating values as the probability, then there should be actually two characteristics. So when you when getting these floating values, their vectors, to call that as probability, you have to have these two conditions. First thing is each element, they have to larger than zero. There is no negative probability. Each values that should be larger than zero and also smaller than one. Okay, but normally we skip this part. So each element have to be larger than zero, and their sum should be one. Okay, so the sum of random variables that should be one if they are probability. Okay, and each element have to be larger than zero. Okay, but actually there's no guarantee for uh, these intermediate responses. We cannot have any way to control those scales. So sometimes this is frequently, not kept. So we can easily keep these characteristics by involving this kind of softmax layer at the end of the network. So when applying the softmax, we first apply exponential for each dimensions. So this yi is indicating this each dimensions of the vector. So this would be y vector. This entire output would be y vector, and each entry will have this kind of I index. So we can denote each entry as yi. So here we apply exponential for yi because we want to secure each entry to have the value larger than zero. When you apply exponential, then each value will have anyways having the values larger than zero. And also you will normalize each value by summing all other, the exponential applied values. Then each entry will now have some normalized value, and their sum would be one. Okay, so y should be here. Okay, y, and each entry denoted as yi here, and then we apply this type of softmax layer. Anyways, this operation is also differentiable, so we can interpret this formula as the layer. So this type of intermediate responses, which is not bounded, by applying the softmax layer that first apply exponential and apply the error normalization, then we can secure this vector whose entry is larger than zero and whose error sum is one. Okay, so now we can call this vector as the probability vector. So if you want to train your network towards the multi-class classification task, then after this, after getting the final response, you have to apply this type of softmax layer. Okay. And then the thing you have to do is use these cross entropy laws to train your entire network. Okay. So cross entropy laws. It has some many interpretation, but the simplest interpretation would be interpreting that as the extension of this binary cross entropy laws. Okay. So this is the ground truth, GT. P is the GT here. Q is your prediction. And this form is actually same. You can interpret it as same as this loss function. So this is actually y(n), ln z(n). This is ground truth, and this is the prediction, and there is log between that. And this is the ground truth, log between this P and Q, and this is the prediction. And there's minus sign, and you have to sum them across all the possible semantic classes, okay? So this is actually the cross entropy loss. And P is actually the ground truth, which is the constant value, okay? P, the ground truth for each sample will not be changed, okay? But you can make predictions close to ground truth, or anyways, you can vary these Q values according to your network parameters, okay? And you can, simplify this formula, into these two terms, okay? On purpose, you will involve P of X, okay? And then, this is actually, how to say, if there is minus sign here, then this would be PX, QX. So these are, deleted each other, and only this part will be remained. But this is the simple mathematics. Anyways, doing this type of trick, you can divide the original form into these two types of term. And you can, because P is fixed across the training stage, this would be the constant term. And actually, this part in mathematics, you can interpret it as the carrier divergence between P and Q vector, okay? And actually, this carrier divergence is minimized when this P is same as Q, okay? So it is also indicating that by minimizing this type of cross entropy loss, Q will be same as P, because that's actually the minima of this function. Okay? So you have to feel that this cross entropy loss can be used make this Q vector. Actually, Q and P both are vector, okay? And P is one hot encoded vector. So for example, if there is 10 classes, then this will have 10 values, 10, 0, or 1, but 1 is having just one ones for this, among the other 0, okay? So, if their ground truth class is 2, then it will only have 1 here and have all zeros for rest of the vector, okay? That is P, actually the ground truth, okay? We already know which is the ground truth among all other classes. So P would look like this, only having 0 or 1 and having just 1, 1. And remaining entry, it will have 0. Okay? And Q is having some continuous values, but because we apply softmax at the last layer, so their sum is, we can say their sum is 1, and their values are all larger than 0. Okay, but actually by using this cross entropy loss, we can make this Q close to this P ground truth value, okay? Are you guys following this? Okay. So anyways, this, when Px is Qx, if their two values are same, this carrier divergence term becomes minimum. And because this is constant, so the entire cross entropy loss, that also becomes minimum. So, reversely, we can say by minimizing this loss, this term is minimized, and minimizing this is equivalent to making P equal to Q, okay? Okay, and also you can implement this cross-entropy loss using the cross-entropy loss function already implemented in the PyTorch, okay? So this is the use case. But one thing maybe you may frequently confused when using the cross-entropy loss. I mean, the loss looks like this. So there should be ground truth and your predictions, okay? And target looks like this. So you will have the discrete integer rather than having this type of one-hand encoded, this kind of one-hand encoded vector. You will define their target array as this kind of integer value, and your predictions might be some this kind of floating values, okay? Having this dimension. So, sometimes people sometimes become confused. Uh, this target should be also a 3 by 5 dimensional vector, but this is actually easy way to implement the cross-entropy loss because their discrete integer is only meaningful. So this PyTorch is providing us to just use these meaningful integer values as the GT, but sometimes this feature makes us confused. So anyways, you have to experience this when implementing maybe assignment 1, okay? Anyways, don't be confused about this. And later, I will also explain how to implement the CNN architecture, whose name is LUNET, for the image classification task. Okay, so this LUNET was quite old CNN architecture, introduced in 1998, and at that time, this deep learning architecture works very well, but there was some problems called as generalization. So this CNN works good for some of the small scale data, but there was a problem that this deep learning architecture CNNs are not extendable to bigger scale data. So maybe overfitting, you may familiar with this. There are some problems like this. So, but nowadays, there's some problem inside the architecture. They are using some nonlinear layers, which is not fully differentiable, and also their scales are small, and their data is also limited. But nowadays, we are improving the regularizer, such as the nonlinear functions inside the deep architecture, and also we have enough resources using the GPUs to make the big scale, large scale data to be usable during the training. And also we can use some data augmentation during the training. So that actually tackle this overfitting phenomenon. So now we are making these deep architectures generalizable to many, many tasks. But at that time, it was not like that. So people think this is the limitation of the deep architecture and cannot be usable for some new tasks. And then after this LUNET architecture, people turn around to the shallow learning architecture, such as the SVM. But after that, in the year of 2012, the AlexNet appeared, and it solves this kind of overfitting phenomenon. And after that, the research is becoming again towards the deep architectures. Okay. Anyways, this LUNET architecture is very early stage deep architecture, and this is only using this type of very small scale images, also their grayscale images. Okay, and initially this LUNET architecture is proposed to tackle this MNIST data set I already told here. So given this small scaled image, actually 28 by 28 by 1 dimensional grayscale small images, what they wanting to achieve is to classify each image into digits the images are having. Digit classification is what this MNIST data set is doing. Okay. And anyways, in the middle, they are having convolutional layers, okay, that I mentioned already. And here they are having FC layers, okay. And their output is 10-dimensional vector because there are 0 to 9 digits, okay. Their aim is to classify, I don't know why here there are A character, but what they exactly doing is using the images having digits and classify them into 10 classes, which means their digits. Okay, that's the what LUNET architecture is doing. And I will explain one by one. And this is some hyperparameters. Okay, we have to import some of the libraries and also have to predefine learning rate and batch size and number of epochs. The batch size, some of you are not maybe familiar with what means this batch size is. This is the multiple image unit, okay? When using GPUs, we will parallelly process the data samples, and we will parallelly process 32 images together at the same time, and for efficiency. So this batch size is meaning that. So we will parallelly process 32 images, and this image size is the image dimension, and number of classes, we will have 10 classes, okay? This is some hyperparameters we will use. And this is the LUNET architecture, okay? Same as before, we define this LUNET class, and there will be two methods, the constructor and the forward method. And here, there are two types of variables, the layers defined. The first part is the convolutional layers, okay? Having conv2D and pooling and tangent hyperbolic functions in the middle. Okay, that's actually same as we showed, but at the early stage, their tangent hyperbolic or sigmoid activation layers are frequently used, and later we use ReLU layers. Okay, and average pooling at the earlier CNN architectures, we frequently see there are average pooling, but later we see that max pooling is more robust. But anyways, this is the early deep learning architectures. This type of activation and poolings are used. Okay, and then later you can see there are linear layers and some nonlinear linear. Okay, and the last dimension that have to be coincide to number of classes. Okay, and forward function, that's also same as before. First, we apply convolutional layer, and then doing the flattening and apply the fully connected layers. Okay, this is the definition of the LUNET. And okay, I have to explain this maybe next time. Okay, I will show you how to implement this LUNET for the multi-class classification task in the maybe this Wednesday. And also I want to notice that there will be quiz one in maybe next Monday or next Wednesday. Okay. So if we finish the remaining part by this Wednesday, we will have the quiz maybe next Monday. But if we cannot finish the remaining materials by this Wednesday, then we will finish it next Monday and then take the quiz one next Wednesday. Okay. Anyways, please prepare for this quiz one. The materials would be covered for, the one this is the lecture 3, okay? Lecture 1 through 3, that would be the material for quiz 1. So please review all the things, okay? Okay, for today, let's finish here and see you this Wednesday. Okay, thank you.